Okay, this screencast continues our discussion of step response based on pole locations, where we have a dominant complex conjugate pair of roots, or pair of poles, and yet there's a nearby real zero that's going to affect our response. Okay, so let me draw a picture of what this situation looks like. We have the j omega axis like before. We have the real axis and a pair of complex conjugate poles. And so that gives us the transfer function. And once again, we're looking at normalized frequency. So omega n is 1. And so we'll be looking at s squared plus 2 zeta omega n s plus omega n squared. Okay? Now we're going to add in the numerator a real zero. Okay? So as we did before, we're going to make this s over alpha sigma, okay, plus 1, and we're going to let sigma equal zeta omega n, and if omega n is equal to 1, that would just be zeta. Okay, so effectively what we're doing is we're drawing a line here looking at this distance sigma, and when alpha is equal to 1, we're going to have a 0 right here at sigma. Okay, but when alpha is equal to, say, minus 1, that would put it over here in the right half plane. Remember, zeros can be in the right half plane. This doesn't make the system unstable. It's only when the poles are in the right half plane do we get something unstable. So if I was looking at negative values of alpha, this would be minus 1, this would be minus 2, alpha equal minus 2, alpha equal minus 3, and so forth. And that's going to affect the response. So we can take a look at that. We can also make alpha equal to positive values of 1, or fractional values, so we could have alpha equal 0.5, alpha equal 1, alpha equal 2, alpha equal 3, and so forth and so on. So we're going to take a look at both cases when we run a Matlab simulation. Okay, so I'm going to rewind this back to alpha equal 1. And remember, the reason we wrote things like this form for the 0, okay, I want to once again cover that s over alpha sigma plus 1 equal to 0, that gives us the 0 location. We can solve for s and we get minus alpha sigma. Okay, so that's the 0 location. We write it in this kind of strange way because if I was looking at the DC gain and I substitute in s equals 0 for the DC part, to get the DC steady state response, the contribution from the 0, you'd plug in a 0 here and you'd still get an overall gain from the 0 term of 1, so it doesn't change. Okay, here's the Matlab calculations and simulations that we're running. I guess actually it's not really a simulation, it's a numerical solution to the step response. Okay, once again, we start with defining a transfer function object, and now I'm going to give this various values of alpha. Because these alphas are negative, from the previous video, that means we have right half plane zeros, and so we're starting close to the j omega axis and moving that 0 further and further to the right. Okay, so this would be a 0, for example, at s equal minus 3 sigma times alpha. All right, and so let's move forward from there. We're choosing a specific value of zeta for this. You can change that value of zeta and see how it would affect the response, but zeta equal 0.4, that gives you a little bit of an overshoot in a natural ideal second order step response. Okay, as we move down, we see that what we needed to change was the transfer function. And so here's the overall transfer function, and you'll notice that in the denominator now I have the 0 location at zeta times alpha. All right, so we're going to step through that in a loop, just like we did before, and we can see the effect on an ideal second order step response in the case where we have nearby real and right half plane, a real and right half plane 0. Okay, so let's run that. There's the natural response in the solid blue line. Notice what happens when you have alpha equal minus 0.5, you get sort of an extreme reaction in the wrong direction and a lot of ringing. So this would be a bad thing in most control situations. As we move alpha a little bit further out to the right, that effect still is present. It moves in the wrong direction and we get some overshoot and the system is slowed down. So you see that's not good in most senses. All right, the effect diminishes though as we increase alpha. So by the time you get out to an alpha of -5, which is the real part of the 0 is 5 times sigma, that effect is less, and we're seeing something closer to the ideal natural second order response. Okay, so that gives you an idea of the effect of a right half plane 0. Okay, so let's go back and change this to the situation where, get rid of this figure. Okay, we're going to change the alpha values. Let's go with 0.5, 1, 2, 3, 5, 9, 10, 100. We're going to move the 0 value further and further off into the left half plane and take a look at that result. Okay, so I'm going to run that. There's our natural, our ideal second order response. You see, if I have a 0 that's at 0.5, I get a lot of overshoot, just a tremendous amount of overshoot. That effect is less and less as I move the 0 further and further out into the left half plane. But you see, there'd be a detrimental effect of having a 0 that's near that complex conjugate set of poles that's supposed to be the dominant poles. Okay, so hopefully you can follow that away in your memory banks, and as you design a control system, when you see zeros start to creep nearby or poles starting to creep nearby dominant pairs of poles that you're trying to use in your design, you have to be aware it's going to make a difference on the response.